I wanted to show one more example of, or an application of where magnetic forces are used, and it's a very important application. And I've got some notes in here that are describing how an electric motor works. Here's a simple animation that's showing how this works, and I want to draw your attention to a couple quick things. They have been, or you have been asked to explain these on diploma exams, to explain parts or how a motor works, and this is kind of the process that you would go through. This is what we call a DC motor, meaning that the current's always moving in one direction from the battery, so that we have to include a split ring commutator, brushes to allow for current to switch directions in here. So I've got a few really important things on this slide that I'm going to go through over the next couple minutes in terms of how to explain how a motor works. Basically, there's going to be a direction of rotation, and that'll depend on how your magnetic fields are orientated and how the current travels through this loop of wire, and you'll see it in a second. The commutator, the whole reason why the split ring commutator is so that you will see the current travel consistently on the north side in one direction, consistently on the south side in the other direction, but the loop will continue to flip. So as a result, the direction on the loop on one side will be in one direction. When the same side of the loop goes to the other side, then it's in the other direction. So the loop reverses its current every half turn is how they describe it. And that's what I have in your notes. The loop and the current reverses every half turn. Some people tend to mix that up and say it's an alternating current. That's not true. The current's always moving in one single loop, but because the loop is in contact with the other brush, that's why it changes its current. The other thing that's going to be very important in here is to understand that yes, we have a set of permanent magnets, and it is the current in the loop moving that's going to cause this thing to rotate. And one important thing to note is that when the loop is perpendicular and the current is perpendicular, then you will have a force. When it's parallel, like it is in this case, you will have no force. And if I can turn this on and let it spin for a minute or so that you can see that, you'll see that, I know this is kind of a simplified version, but notice on the north pole, the red magnet, the current is always traveling upward, no matter whether it's the red side of the loop or the blue side of the loop. But if you look on the south, it's always traveling in the opposite direction, no matter whether the loop is blue or red. But again, if you were to follow the red loop around in its circular motion, it is going in one direction up and in the other direction out. So the current in that loop does switch every half turn. Note that when it's sitting at the top, I don't have current running through it. There's a break because of the brushes, and because there's no current, there's no force. So when you use your left hand rule and you were to think of the loop by the north pole of the magnet, the current's always going into the page at that point. The magnetic field always goes from north to south, so you could see that on this portion where the arrow's pointing, you'll see that the force will always want to push it upward. And if you look at the loop on by the south pole of the magnet, the force will always be down because the current's out of the page. The magnetic field is from right to left, so the force will be down. So on one side of the loop it's pushing up, on the other side of the loop it's pushing down, and that's what causes that rotation. Watching that video on the motor effect in lesson 2, this may make a little bit more sense after watching that video. If not, maybe go back to lesson 2 and watch the motor they have in that video. It's a little bit more detailed than this little animation that I've created in this case. One other thing students should note is this little section of the loop that I have at the back, because that current is traveling in the same direction of the magnetic field. I'll try and see if I can stop it there. There we go. At the back, you might be thinking, well, what's the force on this section? Because the current is traveling in the same direction as the magnetic field, at the back of the loop, at the front of the loop that's inside the magnetic field, there's no force in this little piece, and this big piece at the back, because the current's traveling in the same plane as the magnetic field. Therefore, no force. The current has to be in a perpendicular direction to the magnetic field to experience a force. The instant the current and magnetic field are in the same direction, no force. So as soon as two of those three are in the same plane, there will be no force as a result. And that's how a simple motor works. Now, what they do, if you have to turn a larger object, that little rotating loop is going to cause kinetic energy. That kinetic energy can be converted into other forms of energy. And that's basically what a motor does. It takes electrical energy and creates kinetic energy. And you could turn whatever you want. For example, I worked on my washing machine a couple years ago, and it's basically a big loop and some very powerful magnets. And what it is it's several thousand loops of wire. More and more loops of wire means that you have more and more current, means that you have a stronger magnetic force, and you could turn a much bigger object, like an entire drum full of laundry and water. So if you want to make a more powerful motor, you would have more loops, or you could have a stronger magnetic field, or you could have more current. That's why some big machines tend to have really thick cables and really those special prongs that will allow more current to be delivered, like your stove or like your dryer, and they need a lot of current for making that drum turn. Really powerful magnets also help to increase your magnetic force. So a strong magnetic field, and usually in for example, my washing machine, it has a magnetic or magnets in all directions, so the force just keeps getting stronger and stronger and stronger as a result of this thing turning. And that's how the basics of a motor works. A DC motor will have a split ring commutator and brushes. An alternating current motor will not, because the current will be back and forth in alt AC, and it does this on its own. Whereas a DC, you have to use a commutator and brushes so that you get the current to split every half turn.